Welcome to 8.3 in Math 31, where we talk about some logarithmic functions. Most of this is going to be review from Math 30-1, Chapter 8 there. So that's a good thing. We're not really breaking too much new ground, although we will a little bit later. We're going to talk about a different base logarithm that we use in calculus. This first bit talks about the horizontal line test, which will tell us if the inverse of what we're looking at is a function or not. They introduce some terminology that I'm not overly worried about you using. It talks about this function being one-to-one. It's just the idea that, one input results in one output, and every output only corresponds to one input. And that means that we could take the inverse and it would still be a function. We teach you the horizontal line test in Math 30-1, so hopefully you still remember that. That is just the idea that if I look at a graph and I draw a horizontal line, if it intersects at only once anywhere, then we know that the inverse of that graph will be a function. And they ask us to test if that property is true by basically getting us to graph, I hope, a relatively simple exponential function that's going to look something like this. It is exponential growth. If we wanted a few points on there, just keep in mind that x is the exponent, y is the value of 4 to the power of that exponent. I do always like talking about that we do know that anything to the power of 0 is 1, so 0, 1 is the y-intercept. There is no x-intercept, and that is because we have a horizontal asymptote at y equals 0. Okay, to do the inverse then, what I'm going to do is I'm going to take the original function, y equals 4 to the power of x, and perform that kind of inverse operation or inverse step, which is to swap the input and the output. So x becomes 4 to the power of y instead, and in order to graph that, the best way by far is to take that particular exponential form and switch it into log form, which is that y is equal to log base 4 of x. Hopefully you do remember how to do that still, switch from log form to exponential form. I know I've said this a couple times already in Chapter 8, but if you are struggling with some of these logarithms, do exploit the fact that all of the Math 30-1 instruction is on my YouTube channel. So do take a look and maybe watch a couple Chapter 8 videos. We certainly talk about how to go from exponential to logarithmic form and a few other things. Now, depending on what calculator you're using, you may not be able to graph that, which is a bit of an issue. And so what we talked about in Math 30-1 is that if I have, I'm going to make that an a instead, log base b of a, I can write that as log base c of a divided by log base c of b. And that's a really important thing because when you look at your calculator has a log button, and unless you have an 84 and beyond, that is only base 10. So if we want to check what y equals log base 4 of x looks like, on our calculator, we could write in or type in log x over log 4. And because I haven't written the bases there, that's our default base, which is base 10. Now, I don't want to belabor too much, but when we do graph y equals log base 4 of x, or log x over log 4, what I get is this. This logarithmic function, when the argument of the logarithm, so when x is 1, y is equal to 0. And what we see happening on my black graph there is we would also have an asymptote, except it would be at x equals 0. But the important concept or conversation we're having here is, does the horizontal line test work? And it can get a little confusing because there's a couple different line tests, but the idea is that if I draw, and I'll just draw a horizontal line right here, if I take that blue horizontal line and I put it anywhere on the red function, we see that it only crosses it once, which means that it will also only do so on the black function. Now, really what I'm trying to show here is that if the inverse of a function is a function, then the inverse of the inverse takes us back to the function as well. So when we do that horizontal line test, it is one of those tricky concepts that it shows us if the inverse is a function. But if we do the horizontal line test on the function, then we can check that as well. One thing I would like to point out is that if I change that to a vertical line, this would clearly show me that the red graph is a function, and it would also show me that the black graph is a function. Some students struggle with the idea that, and this is my drawing, it looks like that black line became vertical there. It isn't actually vertical. It just has an extremely large slope, especially as we closer and closer to that y-axis. Okay, they did want us to talk about domain and range though, so it's important we do that. So we had two functions, and I'll write them here. We had y equals log base 4 of x. I'll try to color code it a little bit. We had, oh, I forgot already, y equals 4 to the power of x. All right, exponential functions, typically students are more comfortable with. The domain is that x can be any real number. There's no restrictions on the exponent. But if you do look, and I'm not going to track up so I don't scroll too much, but looking at that red function, we do see that y is going to exist, and I'm going to do interval notation, I think, because it's better. It's going to exist from 0 to infinity, but really important that we put that round bracket on 0, because y is never actually 0. It approaches 0, but it never actually becomes that value. And I always encourage students to remember that you cannot put an exponent on a number and get 0. And that's a really important conversation. Now, there's a caveat there. You can put an exponent on 0 and get 0. 0 to the power 4 is 0. But that's not what that question was saying. Okay, for my log function, and we push this a lot in 30-1, because these two are the inverse of each other, it does literally mean that their domain and ranges switch. So now we have that x exists from 0 to infinity and is any real number within, and I'm going to have that y is just an element of the real. So looking at those domains and ranges, I think it's always important. I don't want to draw too much, but it is the idea that the domain of my one function became the range of my inverse, and the range of my original became the domain of my inverse. And we talk about that a lot in 30-1, but I think it does bear repeating just because of how important it is. All right, the next kind of part of these notes wants us to examine how the base affects the graph. Oh, I scrolled too many. Affects the shape of the graph. Now, I did mention that it's really important that anything to the power of 0 is 1. And what that means is that all 4 of these graphs will have the same x-intercept, which is 1, 0. Now, essentially what's happening when we change the base is that we are really stretching horizontally, and that's a conversation that we could talk about in detail. You could also write it as a vertical stretch. There'd be nothing wrong with that, but the basic idea is that the smaller the base, the quicker or rather I guess the slower the slope approaches 0, and it never actually hits 0, but I'll draw these because I think that's the best way to see it. So this guy right here is going to be when the b is equal to 2, so that's the base of the logarithm. And again, it is going to go through that point, 1, 0. If I were to make that base 3 instead, what's going to happen, and it's really important that it really is doing the same thing. It's just that it's doing it maybe quicker is a good way of describing that. So that would be where b is equal to 3. They both have that same vertical asymptote. If I draw where b is equal to 5 now is next, we would see another similar shape happening here. That would be b is equal to 5. I'm exaggerating these a little bit. It's worth mentioning. And then the last one would be where b is equal to 10. And I would always encourage students to think about why that is. And I think looking at the next point is the most useful conversation. So we know that when x is 1, y is 0, what value of x results in a y of 1? And that's a really important conversation, that if you look at any of these graphs, remember that you could switch them. This is 2 to the power of y is equal to x. So if I want to know what x value results in a y value of 1, I could just put 1 into the exponent. And we see that on this black graph, again, trying to exaggerate just a little bit, I would have the point 2, 1, because 2 to the power of 1 is 2. On my red graph, I would have the point 3, 1. The blue graph, and I'm not going to be able to fit it in here, we won't really see it, I would have 5, 1. And then finally that green graph, and again, I'm not doing this justice due to how different all of these are. The green graph, and I'll just put an arrow somewhere over here, would have the point 10, 1. And I think that's probably the easiest maybe mnemonic to remember this, is that the larger the base, the closer to the x-axis it rests. And I think that's probably maybe the best way to think about what's happening to these functions. Okay. It then wants us to sketch a bit of a different function. There's certainly a lot of different ways of doing this. I think the best way by far is to say that f of x is y equals log base 10 of x, horizontally translated 3 to the right. And this Math 31 course has really endured a few different -1 or pure courses, but it's really important that we teach transformations in all of those because of how useful that is. If you know what y equals log base 10 of x looks like, which I don't think is a very big stretch, we drew it on the other shape there, or on the page, I should say. We know that this is going to go through, and I'm going to put those points right here. We would have the point 1, 0, then we would have the point 10, 1, then I would have the point 100, 2, and I'll just put 3 dots at that point. When I do transform it, so y is equal to log base 10 of x minus 3, what I'm going to have instead is, because I'm moving these 3 to the right, I'm going to have the point 4, 0, and 13, 1. And this doesn't seem much of an impact, but we would have 103, 2. And effectively, like we've talked about so many times in the 30-1 course, that's going to shift the graph 3 units to the right. Now, I want to include both of those on here just so we can see to compare. But what that red graph would look like, really importantly, it's just a translation. So the shape hasn't changed, and we'll talk about why that matters in calculus here, what that's going to look like. And let me draw the asymptote because it's going to be tricky to really see the change if I don't. This asymptote vertical, so it occurs at x equals 0. The new asymptote, let's go 1, 2, 3, it's going to happen right here. That's going to be at x equals 3, and then my red graph looks something like this. All right, now the reason why I talked about shape there is the black graph and the red graph would actually have the same derivative. Or I shouldn't say the same derivative. What they would have is that the slope of that function is ultimately the same. It's just occurring at a different location. And we'll see that when we actually start taking the derivative of these. The question does want us to do domain and range. I always like pushing the algebra way of doing domain. The inside of the logarithm, the argument of the logarithm, has to be positive. So x minus 3 must be greater than 0. That means that x must be greater than 3. So for my domain, I'm going to say that x exists from 3 to infinity with a round bracket on both, and it's every real number in between. And then the range, a little bit easier, y is just going to be any real number. That graph does continue forever upwards and downwards. Last part then, it's always important to include these if they're there. We have a vertical asymptote at x equals 3. Right, that hopefully, hopefully those skills from 30-1 you still have with you. It's going to be really important that we know some of the basics of logarithmic functions because we are going to be looking at, dealing with their derivatives and looking at them, involving rates of change.